Welcome back. In this lecture video, we continue looking at stratified random sampling, and in particular we're going to be looking at making inferences for the totals of finite populations. We'll start off by looking at inference for totals of population strata that comprise the population. So let's look at estimation of a stratum total. An unbiased estimator of tau sub j, the total of the jth population stratum, is denoted by tau hat sub j. It's equal to, there are a couple different representations here, the size of the jth stratum, cap n sub j, times the unbiased estimate of the mean of the jth stratum, which we're denoting by mu hat sub j. And that's also equal to cap n sub j times the sample, the mean of the sample from stratum j. Now the variance of the sampling distribution of tau hat sub j, the estimator of the jth stratum total, first it's denoted by sigma squared sub tau hat sub j, or also var of tau hat sub j, and it's equal to this expression here. So cap n squared sub j times the quantity, and this is a ratio, cap n sub j minus little n sub j over cap n sub j minus 1, and then 1 over the size of the sample from stratum j, little n sub j, times the variance of stratum j, so sigma squared sub j. Once we have that, once we have the variance of the sampling distribution of tau hat sub j, we take its square root to get the standard error of tau hat sub j. All right, and so that is given here. Now, again, we don't know, well, we may not know the stratum variances. All right, in most situations we would not, so that we would have to estimate the sigma squared sub j, or the sigma sub j, from the data. All right, and so we can't calculate, without that information, without knowing what these are exactly, we cannot calculate the actual, the true variance and standard error of tau hat sub j. And so in the absence of the actual values for the variance and standard deviation of the jth stratum, we'll have to estimate the variance and estimate the standard error. So that's what we're doing on the next slide. All right, we are using an estimate, incorporating the estimate of sigma squared sub j in these formulas, and then expressing it in terms of the sample variances. So an unbiased estimator of the variance of the sampling distribution of tau hat sub j, which is, again, the estimator of the jth stratum total, is given by this expression. We could also express it in terms of sigma hat squared sub j, but this is expressed in terms of the stratum sample variances. All right, so once we have the estimated variance, we take its square root to get the estimated standard error. And again, let me just point out that sigma hat squared sub tau hat sub j is an unbiased estimator of this quantity on the previous slide, sigma squared, the true variance of tau hat sub j. So we're not able to calculate this without knowing what the stratum variances are, but we can estimate it, and this is an unbiased estimator. Now, once we have that, we take the square root, we get the corresponding estimator of the standard error of tau hat sub j. All right, and so that's given here. It's just the square root of that quantity there. Once we have that, then we can multiply that estimated standard error by 2 to get our approximate 95% margin of error that is associated with tau hat sub j. All right, so that's given here. And then once we have the margin of error, we can use it in conjunction with tau hat sub j itself, the point estimate for tau j, to come up with an approximate 95% two-sided confidence interval estimate for tau sub j, given here. All right, so just again using that same approach, that same principle, all right, that we've been using. All right, we find a point estimate first. Then we have to identify the form of the variance of that point estimator. Once we have the form of the variance, we take its square root to get the form of the standard error of the estimator. But then we'll have to estimate those quantities because we're typically not going to have the information required to calculate them exactly. So we have to estimate, as in this case, the stratum variances. Using the data, we come up with an estimated variance for the point estimator, an estimated standard error of the point estimator. Once we have that estimated standard error, we can multiply it by 2, right, to get our approximate 95% margin of error. And then we subtract that margin error from the point estimate to get the lower endpoint for the confidence interval. And we also add that margin of error to the point estimate to get the upper limit for the confidence interval. All right, now let's move on to inference for the overall population total, which is really what we're after here. All right, so we can make inferences about the individual stratum totals, but we want to also make inferences about the overall population total. And so an unbiased estimator of the overall population total using, again, stratified random sampling is first denoted by tau hat. And we can compute that in a couple ways. First, n times, remember n is the total population size, n times the estimate of the overall population mean, right? That estimate is denoted mu hat. Or we can calculate it this way, this weighted sum of the individual stratum sample means. All right, so either way, we'll get the same answer. Now, associated with this estimator, tau hat, the estimator of tau, this is a random variable computed from sample values. It's a random variable, so it has a distribution, and that distribution has a mean, and it has a variance and standard deviation. The mean of its sampling distribution is actually tau, right? And that's why we can say that this is an unbiased estimator for tau. The variance of tau hat, the form of the variance, is given here on the next slide. So the variance of the sampling distribution of tau hat, the estimator of the overall population total, is denoted by sigma squared sub tau hat, also denoted var of tau hat, and it's given by this expression here. All right, so you should recognize this. Each of these components is the estimate of the corresponding stratum total. All right, so we're adding those variances up to get the variance of tau hat itself. Once we have this, we take its square root to get the standard error, the actual standard error of tau hat. But again, unless we know the stratum variances, we cannot calculate these quantities. So we would have to first estimate the stratum variances and then plug them in and come up with the estimated variance and the estimated standard error of tau hat, which is what we do here on on this slide. All right, so an unbiased estimator of the variance of the sampling distribution of tau hat, the estimator of the overall population total, is given by this expression here. And so again, this is expressed in terms of the individual stratum sample variances, all right, the S squared sub j's. We could also represent this or come up with a representation utilizing the sigma hat squared sub j's, the unbiased estimator of the stratum variances, but this is in terms of the sample variances. Once we have this, we take its square root, all right, that gives us the estimator of the standard error of tau hat. So sigma hat sub tau hat, the standard deviation or standard error of tau hat, all right, is given by that expression. And again, once we have this, we can multiply it by 2, right, to get the approximate 95% margin of error that is associated with tau hat. And then once we have the margin of error, again, we use that in conjunction with the estimator, tau hat. We subtract the margin of error from tau hat. We add the margin of error to tau hat to get the the lower and upper confidence limits for tau. So again, the objective here is to estimate the overall population total, which is denoted by tau. All right, we come up with a point estimate of tau. That point estimate is denoted by tau hat. That represents our best guess as to the true value of tau, expressed in terms of a single value, but we know that it's probably not exactly equal to tau hat, and so we want to construct a confidence interval as well. So this is how we do it. All right, let's look at an example, example 8. So continuing with the advertising example, estimate the total number of hours per week spent watching television by the households in the county. Compute the margin of error associated with this estimate. In addition, construct an approximate 95% confidence interval estimate of the total. Okay, so using the data that we have been utilizing from previous examples, all right, we can calculate a point estimate of tau. And so the point estimate of tau, which is denoted by tau hat, I'll use the formula or the version, the representation of this formula equal to cap n times mu hat. You'll recall that cap n is 310 households in this county. All right, the estimate of mu hat that we came up with was 27.675, and so multiplying those two quantities together, we get 8,579.25. So that's our estimate of the total number of hours spent watching television by the households in the county per week. Now, we ultimately want to construct a confidence interval for tau as well, and so to do that, we need to calculate the margin of error. And to calculate the margin of error, we need to come up with the estimated standard error of tau hat. And so this is the formula that I'll use. And you can see the quantities plugged in there, and so I'll let you review that. Ultimately, when we do the calculation, we come up with an estimated standard error of tau hat of 435.053. If we multiply that by 2, we get 870.11. We then subtract that from our point estimate to get the lower confidence limit for the confidence interval, and then we add this margin of error to the point estimate to get the upper end point. And so we get an approximate 95% confidence interval estimate for the total number of hours spent watching television per week in this county, ranging from 7,709.14 hours up to 9,449.36 hours. So that is how we do that. It's very similar to the process for estimating the population mean, but it's just expressed in terms of the total. Now, one thing I would just point out is that there's a lot of calculation going on here, and the more calculations we do by hand, the more opportunities to make a calculation error, entering values into the calculator incorrectly, forgetting to incorporate required quantities and so forth. And so I would just say that, be very, very careful in doing these calculations. All right, so that wraps up this lecture video. We'll continue on with the next topic in the next lecture video.